No math classes will meet on Monday. Instead, I know I sent out the schedule for the math retreat by email, but I know emails get buried. So on Monday, you should go to the math retreat, and a schedule of events can be found on the course webpage. So I like organizing it by date like this, but by the end of the semester it means a lot of scrolling. Under math, April 25, the day's events for the math retreat. Take you to a place like this. And as one last announcement, anyone thinking that they might want to sign up for the math retreat competition? Well, maybe I'll try to sweeten the pot. So there are prizes. There is technically a cash prize, but the cash prize isn't big. I think for the winning team, it's like $50 or something. But more importantly, the winning team will get a physical copy of that. The so-called Barth sextic, which, I mean, I can tell you what it is, really. It's the zero set of a polynomial. It's the set of all solutions to that equation. Or I think phi is the golden ratio. Printed out by Professor Amethyst of the math department, who is the same as, previously there were like little plastic thingies hanging in this hallway. No memory of that? Okay. Cool. Radical. Shall we begin? All right, if you want to sign up for the math retreat, there's a flexible deadline of Saturday. And there's extra credit too. So, you know, if you want some extra credit, that's probably the lowest time commitment extra credit in this class. Yeah?
So to go to some of the other stuff, you don't need to sign up for that.
No.
Just the
yeah.
other thing.
Yeah. The schedule is here. Pick some talks that you like the look of. If you want me to give you some recommendations, you can email me and I'll give you some recommendations. Otherwise, go to some talks. Yeah. Cool.
Is it online, or do you have to actually go?
Yeah, it's here. Like, it's not all in this room, but this room will be used. In Hibord 302, there will be some UWEC graduates who are currently grad students at University of Chicago, UW-Madison, and Minneapolis, University of Minneapolis. We'll give some talks and also give a discussion about what grad school is like if you want to come to that. And that'll be in this very room. So take some time, look at that, come to some talks. So what I want to do today is some more discussion of how to use the law of sines. And I want to focus first on just that bit of subtlety about side-side angle triangles. So let's not actually find the values that solve these triangles, but let's just determine how many solutions they have. And to do that, we'll go through the motions of beginning to solve them. So let's look at this first triangle problem. Is there a side and an angle opposite that we know? Yeah. There's the 10 degrees and the 1 unit. That's obviously not as pictured a 10-degree angle. This is not drawn to any sort of scale. But that's okay. So I know these two things. So I know a side and an angle opposite. What other thing do I know about this triangle? I know a side length. So I should be able to use the law of sines to determine the angle opposite. Let's go ahead and do that. So apparently, by the law of sines, the sine of b over 10 is equal to the sine of 10 degrees over 1. And let's go through the motions of beginning to solve this. So if you wanted to solve that for sine of b, what would you do, or what would you get at the end? let's say, I guess it's just like a cross-multiplying thing, right? Multiply the 10 to the other side. Division by 1 doesn't do anything, so I'll just erase it. Sine of b is equal to 10 multiplied by the sine of 10 degrees. And what is 10 times the sine of 10 degrees? Here people are already taking out the calculator, so I bet you have that before I do. 1.7. So apparently this angle B satisfies that its sine is 1.7. Is there anything wrong with that? Yeah, what's wrong with that? It's too big. It's bigger than 1. Does any such angle exist? No. This is bigger than 1. So this has no solutions. No such triangle exists that satisfies those parameters. Let's talk through the next one. So, I guess the setup is the same. I know an angle and a side opposite. So this time sine of b over 3 is equal to the sine of 10 degrees over 1. So what is the sine of b equal to? Right here, 0.52. Cool. Is that a valid output for sine? So it looks like there might be some solutions, and one of them is automatic. One of these solutions will be b equal to the inverse sine of 3 times the sine of 10 degrees, which is whatever it is. And now we have to ask ourselves, is it possible that this angle b might be obtuse? And to check that, look at the side length opposite. Is it the longest side length? Or it might be the longest side length. I don't know that missing side length. So it's possible that this angle is obtuse. So how would you turn that angle into an obtuse angle with the same sine? So one of them is that angle. The other one is this angle. How do you describe that big angle in terms of the little angle? (180 degrees minus). So this has two solutions. (180 degrees minus arc sine or sine inverse of 3 times the sine of 10 degrees. So, in this case, there might be two solutions. 0 solutions, 2 solutions. And maybe before we even start in on the next one, let's just look at that triangle and tell me, if that triangle exists, is it possible for the angle B in this last example to be obtuse? No. The side length opposite is definitely not the longest side. It might be the shortest side, it might not be, but it's not the longest. The side length 3 is longer. So one thing I can see automatically, at most, one solution. B can't be obtuse. But, well, I mean, could we go through the exact same motions to figure out what B is as we did before? Yeah, right? This time it's sine of B over 1 equals sine of 10 degrees over 3. Is that quantity less than 1? Yeah, in fact, you can tell that without resorting to a machine, right? sine of 10 degrees is a small little thing, and then you're dividing it by 3, which makes it even littler. So it's definitely a valid input. So that means there is at least one solution. So b equals sine inverse of sine 10 degrees over 3, which you could then ask a computer to compute for you. And are there any other possibilities for b? No, the other one would be the obtuse option, but we already said that's impossible. So this has one solution. Cool. How does that feel? Does that seem pretty okay? Yeah.
So you maybe said this, so I get the third one we just said, but the second one, we checked that there's two solutions because like there was a possibility of it being obtuse, right? Like
Yes.
is that what indicates?
Mhm.
Okay.
Yeah, so if that angle b were obtuse, the side opposite would have to be the
Like
biggest.
we don't know, so we can,
You don't know if it's obtuse or not.
Okay.
You don't even know if it exists.
so that's how we know there's two solutions?
Yep.
Okay.
And then you can go through and find everything else once you know b. Cool. How do people feel about side-side angle triangles? Nice. So, let's move on to some concrete applications. Let's talk about triangulation. So this is the idea that, like, you have two viewing stations that are some distance apart. They both look out at some object in the distance. It's too far away to measure the distance directly, so they both just draw a straight line to it. And they measure the angle between these lines and the straight line between them. And then they can triangulate the location of this other thing, meaning that they can draw a triangle to tell them exactly where this other object is. And let's see that in practice. Here it is. You and Paige Pierce, top rank USB GGA player, see a flying saucer pass overhead, which is, of course, a perfectly reasonable thing to see. Yes. Top rank player as of 2019. I intended to update these notes with more recent rankings. Stand in a field 30 feet apart and see a flying saucer pass overhead. Both of you measure the angle of elevation. This is, again, obviously not trying to scale. Of the horizontal to that flying saucer. Let's try to determine lots of things. This side length, and the actual height of the flying saucer. So let's go ahead and do that. So I'm looking at this big triangle. What's something in that triangle that you can compute? The third angle. You know two angles, you automatically know the third. There's a secret assumption that I'm making that, like, the geometry we live in satisfies Euclidean properties. If the world we lived in were hyperbolic, which maybe it is, this would not happen. All right, so in that time to stall, how big is that angle? Nice. All right. Now that we know that much information, does it seem easy to find a side length? Which one should we do? I think I'm only going to do one. Distance from you or, oh, and it's mislabeled. Paige Pierce, Katrina Allen, god damn it. Well, all right. Let's find this distance. Let's call that, I don't know, A. So we want to use the law of sines to find A. And let's set ourselves up to do that. Apparently A over the sine of 70 degrees should be the same as 30 over the sine of 25 degrees. Those sure look like angles that I don't see on the unit circle, so after I solve to get something exact, I'll just have to bust out a machine to get a decimal approximation. And that looks really easy to solve, right? If I want to get A on its own, I just need to multiply something to the other side. I do anything wrong yet? Cool. All right, so apparently A is, I just multiply this to the other side. Sine 70 degrees times 30 over sine 25 degrees. And resorting to a computing machine. Sine of 70 degrees times 30 divided by sine of 25 degrees. Apparently somewhere around 67 units. All right, and what are the units in this problem? Feet, cool. Because that 30 is measured in feet. Cool. Does that application seem reasonably useful? Yeah. Let's do one last one. Let's talk about another surveying example. So let's suppose that Alice and Bob measure the distance between each other to be 50 meters, and then they look off in the distance and they see a peak just sticking above the horizon. It shouldn't be sticking above the horizon. If you go too far, then you run into the fact that the Earth is curved. So they should be closer than that if you want triangulation like this to actually work correctly. Otherwise, you have to do some more complicated geometry. Not that's beyond us, just you have to do more complicated geometry. So let's try to determine the height of this peak, assuming this flatness assumption. So I see this much information right now. And let's not try to find everything all at once. Let's just try to find things that we can find. By looking at this triangle, what is something we could find? Or maybe it's hard to even describe. Let's give some things names. You know, call this angle A, B, C. This would be A. Call that big C, maybe that's big D. There's E. Let's just start trying to find some side lengths and some angles. What looks like something that we can find? Angle A, I think we can find. Because this whole angle should be a straight line, so 180 degrees. So what's the angle little a? Nice. All right. Do you now see in this picture a triangle which satisfies that you know a side length and an angle opposite? Calm down. Let's just keep on finding stuff. What seems like something else we can find? The angle B. What is the angle B?
5 degrees.
5 degrees. Cool. What's something else that we can find?
Angle C.
Great. What is the angle C?
55 degrees.
55 degrees. And those are fast, but are people following where those angle computations are coming from? Anyone want to discuss? All right. Cool. So now it looks like we have all of the angles. So that means we should be able to start finding some side lengths. Right now, let's see, we can't use SOHCAHTOA yet. We don't have any of the sides of a right triangle. Let's try to find a side of a right triangle, and then maybe we can go from there. So what side would you like to try to find next? That seems promising. Let's try to find A. Do you know the angle opposite A? Yeah, it's 145. So apparently by the law of sines, A, big A, over sine of 145 degrees. Is there a side and an angle opposite that we know that we can take advantage of? Yeah, great. So let's do that. I know this side length, 50 meters, is opposite the sine of 5 degrees. So cool. Does that look like what basically set up to solve for A? Yeah. Multiply a thing over to the other side. A is equal to 50 meters multiplied by the sine of 145 degrees divided by the sine of 5 degrees. That'll give me the side length A. And we can get a decimal approximation if you want. In fact, if someone already has a decimal approximation, we can record it.
329.1.
Here are 329.1. And I guess that's in meters. Is that the side length we wanted to find though? What is this problem actually asking for? How tall the mountain is. Is that already something I've labeled in the picture somewhere? D. So I want to know how big D is. Alright. Let's see, do you see a right triangle that you could now use to find D? Yeah. Do I know at least one side of that right triangle? Cool. What trig function looks useful? Sine. Or I guess cosine if you wanted to use this angle. Yeah, sine if you want to use that angle. So, by SOHCAHTOA, the sine of 30 degrees is opposite D over hypotenuse A. Does that look easy to solve for D? Yeah, you multiply it to the other side. And then do I know what A is already? Yeah, it's whatever that big complicated looking thing is. But, I mean, it's complicated looking, but I can still just write it down. Sine of 40 degrees, sine of 145 degrees. I'm just putting the angle so they're all together, times 50 meters, divided by sine of 5 degrees. And that's like lots of stuff to write down, but it's just a thing, it's a number. If you wanted a decimal approximation, you'd use a machine. Backed by the people who are already using that machine. What is that decimal approximation?
164.5.
154.5?
64.5.
164.5. Cool. So if you want to measure the height of a mountain, this is one way to do it. It's not much of a mountain. But, I mean, you can't be that surprised given that I just wrote some numbers down. I didn't measure anything. Any questions about the law of sines and its applications? Groovy. So if you remember in that flowchart about how to solve triangles, there were two cases that we just didn't deal with. Well, kind of three. If you have an angle-angle-angle triangle, you don't have enough information. If you know 3 other pieces of information, you should still be able to determine everything, but you need a different tool. Like the law of sines works really well if you know 2 opposite pieces of information, a sine and an angle opposite. Or what if you don't have that? What if instead you know all 3 sides? Or you know a side and angle in the side. Then law of sines doesn't apply. You need a different tool. That different tool is the law of cosines. So let's start it on the law of cosines. So maybe I'll start with this. So the law of cosines is going to try to fix the Pythagorean formula to apply to non-right triangles. So there's a right triangle. What does the Pythagorean formula say?
A squared plus B squared equals C squared.
Nice. Well, what if we tweaked that a little bit? There was a side length A, a side length C, a side length B, but then this other angle wasn't a 90-degree angle. It was something else. Maybe it was a 75-degree angle. That should still be enough information to determine some relationship between the side lengths. That's what we'll do right now. And we'll do it in a way that's very similar to how we got that area formula. I'll say, well, I would be really happy if I saw a right triangle, and I don't. But I kind of do. I can can like split this into two right triangles, right? So let's do that. Let's split this into two right triangles. Start by breaking it up into two right triangles. Drop a line from here to there. Let's call that side length h for height, which is awkward because there will be some hypotenuses that we'll study, which we now won't be able to call h because h has a job. Let's try to study this. So I see two right triangles. Let's study this one on the left. And I'll split this side length up into pieces also. I'll call this side length A0 and this side length A1. All right. So let's use this right triangle to determine some stuff. So you're allowed to know the side length A, the side length B, and the angle theta. Your goal is to determine the side length C. Well, let's start with just the side length H. Given these bits of information, this, and this, could you determine side length H? What trig function looks useful? Sine looks useful. But I wouldn't want to use cosine because I don't know A0 and I'm not trying to find A0 yet. I wouldn't want to use tangent because I don't know A0 and I don't know H, so sine. All right, so it looks like sine of this angle theta is opposite h over hypotenuse b. That look easy to solve for h? Yeah. H is equal to b times sine theta. Cool, that's progress. What about A0? Could I find A0 using something similar? What trig function would I use instead? Cosine, I think. Cosine of this angle theta, using the same orange triangle, cosine of theta is adjacent A0 over b. So A0 sure seems to be b multiplied by the cosine of theta. All right, so you see how I'm just kind of like progressing, finding things that I can find? Like, there's no rhyme or reason to which one I'm picking when. Just if you find everything, then you found the thing you were looking for. Sometimes the art is knowing when to stop, noticing when you found the thing that you actually want to find. So I know A0 now, and I'm given A1. That's one of the things I'm given in the problem. So can I find A1? Yeah. A0 and A1 together should be A. So it looks like A1 should be A minus A0, also known as A minus B times the cosine of theta. And now I'll look at this right triangle. At this point, do I know the height of that right triangle? The blue right triangle? Yeah, it's h, and I have a formula for h. H is b times the sine of theta. Do I know the base of that blue right triangle? Yeah, it's a1, which is a minus b cosine theta. So do I know the hypotenuse? Yeah, a squared plus b squared equals c squared, except the names of a and b are wrong. So, using this blue line triangle, which maybe I can copy down for convenience, side length C, there's side length A1, there's side length H. It sure looks like C squared is equal to A1 squared plus H squared. That seem like progress? Do I already know what A1 is? Yeah, let's use that. Here's A1. A minus B cosine theta, quantity squared, plus. Do I already know what H is? Sure do. B sine theta squared. And at this point, I've achieved what I wanted. this is a formula that will tell you C if you know A and B and theta. I guess you have to take a square root, but that's okay, we can take square roots. Does that look like it is maximally simplified right now? We can probably do something with those squares. Let's do something with those squares. If you want to square this bit out, what do? Do you just square each piece and make a difference? You have to FOIL it, right? Yeah, so let's FOIL that out. See what happens. So C squared is equal to A squared minus AB cosine theta minus B cosine theta A. So that's minus 2AB cosine theta plus B squared cosine squared theta plus B squared sine squared theta. And that's progress, right? There's now these fewer points exploding around. See anything that combines and simplifies in a nice way? What's sine squared plus cosine squared always equal to? 1. Is there a sine squared plus cosine squared in this problem? Yeah, like you would factor out a b squared to get b squared cos squared plus sine squared. So I can replace all of this with just b squared times 1, also known as b squared. So doing that, we wind up with c squared equals a squared minus 2 cosine ab cos, oh, got ahead of myself, 2ab cosine theta plus b squared. Well, that b squared is exactly the thing that's orange above. Groovy. So, some things to notice. Does this look fairly similar to the Pythagorean theorem? Yeah, it's almost a squared plus b squared equals c squared. You're just off by 2ab cosine theta. And maybe I'd even rewrite this so that the a squared and b squared are like next to each other. So the law of cosines says that whenever you know this side, and that angle, you can determine this side by the formula c squared equals a squared plus b squared minus 2ab cosine theta. Nice. And in fact, let's see if this recovers the Pythagorean identity. So if that angle theta were a right angle, a 90-degree angle, what's the cosine of 90 degrees? I want someone to say. What's the cosine of 90 degrees? 0. Perfect. So if you have a right angle, what does that formula become if you plug in theta equals 90 degrees? Yeah, just c squared equals a squared plus b squared. So this does recover the Pythagorean theorem, which is nice. Cool. So, what I want to do with this is really similar to what we did with the law of sines. Let's use it to solve some triangle problems. We'll do some things in the abstract and talk about just like some flowcharty ways of solving problems. And then we'll do some applications with it. Cool. So here's the most obvious thing. So this says if you have something that looks like A, B, and theta, you can find C by the formula C squared equals A squared plus B squared minus 2AB cosine theta. So how many people think that maybe it would be worth having formulas like this and the law of sines on a note card for the test might be worthwhile? Yeah, sorry, I shouldn't have phrased that as a question. That should be a statement. So let's try to use this to solve this triangle problem. So do I know two sides and the angle at which they meet? Yeah, so let's use that. Let's go ahead and, I don't know, 5 can have the whole of A, 3 can have the whole of B, I guess this can have the whole of theta, and C is C. So let's see what this says. This gives us C squared equals A squared plus B squared minus 2 times A times B times the cosine of theta. Oh neat, does that just look manifestly computable? Would people rather go by hand or just do a software machine? People want to see it done by hand? Alright, then I'll just pause for a moment and you will tell me a decimal approximation. Or an exact value, whichever you want. As soon as someone feels confident, maybe has compared with someone around them. So what is that?
1.61.
After you took the square root or before?
After.
After, okay. Cool. That agree with what other people are getting? Or does anyone want me to talk through that in any more detail than the none that I did? Okay. Awesome. Did anyone get something different? Okay. So, here's now this flowchart. So, if you know all three angles, you don't have enough information unless you have something more. If you have two angles and a side, find the thought angle, then use the law of sines. If you have a side-side angle triangle, use the law of sines to find the remaining angle with just the acceptance that there might be 0, 1, or 2 possibilities. If you have a side angle side triangle, you can use the law of cosines to find the missing side. Ooh, and imagine you wanted to finish this up. So once you knew that side, and this angle, and now you found out that side length C, do you now know a pair consisting of a side and an angle opposite? Yeah, so you could use the law of sines to figure out a remaining angle. In fact, you could find either of the remaining angles that way. Let's find the one that we know can't be obtuse. And looking at that triangle, what side length is not the longest side length that we could use? That's not the longest. So I must find this angle next, using the law of sines. That seem reasonable? And then once you know two of the angles, you can find the thought because the two angles have radically high radians. If you know all three sides, well, you can do something really similar to find that cosine of theta. And let's try to do that. So let's try to find some angles in this triangle. All right, which angle would you like to find? Alpha, beta, or gamma? Alpha? Beta. Gamma. All right. Well, it was kind of a tie at one vote alpha, one vote gamma. But the vote for alpha seemed more committed. So we'll do alpha. It doesn't matter which one we do. It'll be the same walk no matter which one we do. So let's try to find the angle alpha. So to find alpha, let's see. Here's two sides that meet at that angle alpha. Here's the third side. So I think I will treat that side length 4 as A, that side length 3 as B, that side length 2 as C, and we'll go from there. So we should get C squared equals, C squared being 2 squared, equals A squared plus B squared minus 2AB times the cosine of the angle alpha. I guess here's one question. Does that look like we could solve that for cosine of alpha? Yeah, let's do it. All right, so I'll go through some of the motions all at once. So that 2 squared will become a 4 minus 16 minus 9 equals negative 2 times 3 is 12 times 4. No, 2 times 3 is 6 times 4 is 24. People with me so far? So I guess the next thing to do would be to simplify the left-hand side and divide. So 4 minus 16 is negative 12, minus another 9 is negative 21. That sound believable? All right. So I see negative 21, and then I guess I should divide over the negative 24. Equals cosine of alpha. Should I do any simplifying before doing the inverse trigonometry? Yeah, negative divided by a negative is positive, so I should do that. 21 and 24, do those have any common factors? Yeah, what's that common factor you see? 3, because that's, I guess, 3 times 7 divided by 3 times 8. So 7/8 is equal to cosine of alpha. And do you remember how there's this like weird ambiguity in the law of sines when we use inverse sine to find the thing? I'm going to try to convince you that that ambiguity can't happen when you use the law of cosines. What types of angles are you allowed to see in a triangle? Like biggest and littlest possible angle. Anywhere from 0 degrees to 180 degrees? Or 0 to pi if you like radians. Maybe I'll exclude endpoints because you can't have a 0 degree. All right, so those are the angles you can see in a triangle. What's the range of inverse cosine? What's exactly that? So, the angle we produce will be exactly the angle we want. So let's take use inverse trigonometry. It looks like the angle gamma has to be cosine inverse of 7/8, which I'm running low on time, so maybe I'll just wrap up this particular computation by saying, well, what is the inverse cosine of 7/8? And maybe I should ask, degrees or radians? Okay, I hold at least one call for degrees. Does this problem specify whether it wants? So, somewhere around 29 degrees. Or in radians if you would prefer something else. 0.5 radians? Is that what I got? I guess that seems right. Nice. So, how do people feel about that application of the law of cosines? Cool. So what we'll do when we meet again on Wednesday, because this class does not meet on Monday, The method group is on Monday. So on Wednesday, we'll finish up talking about the law of cosine. Cool.
Okay, I'm just trying to figure this out. So I might just leave my calculator. So can I just type this in the way it is?
Yep.
Okay, because I'm going to do that. And it's in degrees. Oh, are you doing the...
Yes, I have an idea where you're going to be on that, but keep going. I want to see what you actually type in. I want you to first see
For the second
Oh.
Yeah, I kept hitting 19. I wasn't calculators, so I have no idea.
Yeah.
No.
Unless it's a setting,
Well,
I changed it.
I didn't do the computation at all, right? I just trusted you gave me the result, right?
Yeah.
Let's see. Well, you should, when I stop and say, do people get different answers? This is why I asked.
Yeah, I know it's wrong.
Yeah, me too. That's why I'm like...
Well, even if you are, we should figure these things out. 5 squared plus 3 squared minus 2 times 5 times 3 times the cosine of pi over 3. I know that you put it in degrees,
Yeah.
but it's already in radians, this way I don't have to convert.
Yeah.
Okay.
So why don't you stop me?
Well, I didn't know. I thought because my calculator, yes. And then this one too. Because I got, okay, let me just type it in, 50.
Yeah, so now I'm getting the thing that you said.
Okay, great.
So I'm like, oh, mine's just wrong. I'm just
Five. So I get that.
329? And what was the consensus?
32.91.
42.9.
So do I have to divide? I don't know. I'm just.
That's on the previous page. It's on this page. All right, so 50 degrees times sine of 145 degrees all over sine of 5 degrees. 50 times sine of 145 degrees divided by sine of 5 degrees. Did you say 381? You said 329.
Oh, you typed 58 instead of 50.
Okay, well that will explain why it's reasonably close. 329?
Yeah, so wouldn't it be 32.9? It would be 329.
Wait, you said that. Oh, okay. I think that maybe either I miscommunicated or you miswrote a decimal place.
Oh.
No, I think we agree.
Okay, sorry about that. I was
No, don't be.
obviously thinking that.
If you're going to apologize for anything, it's for not asking the question soon off.
Okay, have a good weekend.
Yeah.